Okay, we are going to get started now. So first of all, hello and welcome. Thank you to all of our presenters and to our wonderful audience today. It is such an amazing experience. My name is Dr. Rachel Peasy, and I am an assistant professor in the PhD in Educational Neuroscience program. I am also the director of the Cognitive and Effective Neuroscience Lab. So today I will be hosting the presentation. This is a presentation put on by VL2's staff and faculty and students. All of the presentations will be very brief. These presenters will be giving a brief synopsis of their studies and their findings and their plans for future research. Thank you for assisting in us sharing our ideas and celebrating the science that we're studying. Thank you for sharing these wonderful findings that we've come across throughout this year. Now I will turn it over to the Chief Research Officer, whose name is Dr. Purna Kushalnagar. Thank you. Purna? Okay, just wait a moment. We're going to spotlight you, Dr. Kushalnagar. Thank you.
Hello, everyone, and welcome. Thank you so much for inviting me to be part of this talks and give opening remarks. I've had it on my calendar for several months, and I'm so excited to see everyone today and all of your work. First, I wanted to recognize and thank a few administrators who are here watching student, staff, and faculty presentations. President Cordano, Provost Lewis, and Dean Rashid. Thank you all for joining us for today's presentation. I also wanted to recognize that leadership is important in two ways. Dr. Lori Ann Petito's leadership and Dr. Graf Mather's leadership over the past year. Thank you so much, both of you, for your support of this program. Over the next hour, you'll watch several different short research presentations from labs throughout VL2, faculty and staff members, including Rachel Peasy, Lorna Quant, Ilaria Bartoletti, Melissa Herzig, Bradley White, who is leading a group presenting from Dr. Petito's lab, and students in the Educational Neuroscience program, Carly Liana, Athena Willis, Casey Spellman, Sarah Kimbley, and about 20 undergraduate and graduate students will be part of this as well. I hope you see, or you don't get caught by the bison when your time is up. Thank you everyone for participating and working hard to get to where you are today. Enjoy the presentations.
Thank you so much. We really appreciate it. Okay. So here you can see an image showing all of our labs. So today we'll be having presentations for many of these labs that you see here. Here is a list of our presenters. So I will be up first and to get us started. So before we start our presentations, I just want to make sure that I have mine set up first and share some guidelines with you. So for our lightning talks today, I want to share with you a bit about the purpose. So today will be a learning experience in sharing scientific ideas in a clear and concise manner, which is a very important skill. Within our labs, each PI works with students, and each of these presenters will be giving approximately 3-minute presentations. If a presentation is a group presentation with several members of the lab, then those presenters will be given 6 minutes. At the end of the presentations, we will give a bit of flexibility. Presenters have a 15-second grace period. However, the goal today is to not be caught by our Bison. If a presentation is over time, then what you will see is this. This means you've been caught by our Bison. So when this slide appears and the Bison comes up on the screen, that's when you know you've gone over time. So the goal, of course, is to not be caught by the Bison. Okay? So with that, I will be giving the first presentation. I'm going to make sure my slides are all set. And I will be using spoken English for my presentation. Okay, we're ready to go. And thank you to our interpreters today.
Can everyone hear me okay? Okay. So as I said before, I'm Dr. Rachel Kesey. I lead the Cognitive and Affective Neuroscience Lab here at Gallaudet, the CAN Lab. And so today, I am going to be presenting to you strategies for remediating math anxiety in high school math classrooms. So in this particular study, we are focused on this question. How can we improve educational outcomes and learning in math-anxious individuals? So past research has shown that more math-anxious individuals tend to underperform in mathematics. So having lower grades in math classes, taking fewer math classes, and choosing fewer math-related careers. So we want to come up with strategies to improve these educational outcomes for these more math-anxious individuals. In this study, we wanted to compare some different intervention and learning strategies. And so we did that in some actual high school classrooms. So we went into 2 schools across the country, tested about 250 students, and these students were enrolled in algebra and geometry classes. So within each class, students were assigned to one of 2 intervention strategies. So we had 2 strategies designed to help the impact of anxiety on performance. The first of which was an emotion regulation strategy. So the idea being here that if we regulate and reduce anxiety, we might be able to improve math performance. We compared this to a study skills intervention designed to improve the way that students approached their math material in their classes. The idea being here that we would strengthen math knowledge to improve math concepts and make these concepts more resilient to anxiety. So we did this study over the course of a school year. During the first semester, we consider this our pre-intervention semester, and we followed students over the course of this first semester, following their grades and tests before the interventions were introduced. Then during the second semester, this is when we introduced our intervention groups. And so we set these up in structured in-class discussions with our research group. And then over the course of second semester, we had questionnaires and follow-up activities throughout the course of that second semester. So in this way, each individual is able to serve as their own control group, where we set up their performance during first semester and then introduce that intervention during second semester. So what do we find? Here, as we go from low to high math anxiety on the x-axis, in the black line, the emotion regulation condition, we see that the more math anxious individuals underperform in their math grades. However, in the study skills intervention, we find that these grades in higher math anxious individuals are improved. So overall, how do we improve these educational outcomes for math anxious individuals? Across both samples, the study skills intervention was more effective in improving performance, and the study skill was effective at reversing anxiety-related deficits in grade performance. So I'm going to quickly thank my collaborators at Dartmouth, my lab, as well as the people who participated in the study, and that's my grace period. Thank you all very much. All right, thank you all. Does anyone have any questions? I can take maybe 1 or 2 questions from the audience while Dr. Bertoletti comes up on screen and gets prepared for her presentation. Any questions about that study? Okay, well, at this point, I will turn it over to Ilaria.
Hello, everyone. You can advance to the next slide. My name is Dr. Ilaria Bertoletti, and I'm the director of my lab, Numeracy and Educational Neuroscience, also called the NENS lab. You can see all the members of my team here. Next slide, please. Our lab looks at how language modality impacts numerical and arithmetic reasoning, both process and acquisition. We study both adults and children. For our children's study, we have a large longitudinal study. And Casey Spellman will be talking a little bit more about that study. We've also set up a new remote study looking at how children use number, words, and signs, and visual spatial-based signs as well. For our adult studies, we're going to be starting a new behavioral study this summer about how ASL supports the idea of processing parity. We also just published an EEG study, and Sarah Kimbley will expand more on that. There was just a dissertation defense using fMRI, and I'll talk a little bit more on the next slide about that fMRI study for adults. This fMRI study was part of a larger project, but Dr. Sullivan, my former graduate student, led this project. We investigated how ASL phonology was involved in supporting mathematical processing. And what we saw is that the language region of the brain was involved for multiplication processing, not only internal talk, but we see our participants with high ASL fluency also recruiting those language regions more. This shows how ASL fluency then supports better processing for multiplication. Next slide. This will have an impact on education policy, training, and different ways that we can support early signers in processing multiplication problems. Thank you. Next slide.
All right, well, that is it. You did not get caught by the bison.
Yeah, I can take questions if we have a minute, and if anybody has them. All right.
Okay, well,
Thank you, everyone.
We do have one question.
So this was a study with adults, so all adults who were early signers.
Thank you. Okay, for our next presentation, Casey.
Oh.
All right, should I advance the next slide?
Yes, I'm ready. Hello, I am Casey Spellman, and today I will be talking about the impact of language acquisition on early numerical cognition. That's something we've been studying in the NENS lab. Next slide. Next slide. Our participants included children from ages 3 to 5 in 3 different categories: hearing English speakers, deaf ASL signers who had early exposure to ASL, and deaf ASL signers who had delayed exposure to ASL, meaning exposure began after age 2. We were investigating the difference between these 3 groups and how their language experience impacted their approximate number system and their exact number concept acquisition. Next slide. We had several tasks for the children to do. You can see them listed here on the slide. We used some standardized assessments to measure intelligence and vocabulary. We used measures of approximate number system understanding and measures of exact number concept. We also used letter and number tests, and we did some assessments of core skills as well. Next slide. In terms of our current status, we have had 36 participants who were deaf early exposed to ASL. There's 21 of them, and then 15 from our group of hearing students. In 2021 through 2022, our data collection has been done in lab, and we will continue to do that with both hearing and deaf participants moving forward. We will go and work with a team in California School for the Deaf Riverside. We've been there before. We will go back next week and next fall. And our goal is to assess them, as you can see, every 6 months over a year period, assessing them a total of 3 times. We're also going to be going to Pennsylvania, to the school in Philadelphia as well. The reason we're doing this study is that we want to have a better understanding of different developmental trajectories for these children. We want to have improved intervention and instruction for deaf and hard of hearing children, and we want to support changes in educational policy for deaf children. And that's it.
You didn't get caught. Congratulations. Okay, any questions for Casey? Okay, seeing no questions.
Thank you.
Very exciting. Okay, for our next presentation, Sarah. Sarah. Okay, Sarah, if you're ready to get started.
I am.
Awesome.
Hello, everyone. I'm Sarah, and today is my 3rd year in the Penn program, and I'm going to talk about this study, the influence of language modality on neural arithmetic processing. Next slide. One important broad question is, how does language experience influence underlying neural networks subtending arithmetic processing? Thus far, the field has only studied arithmetic processing within speaking populations. Therefore, here we're asking if there are different neural signatures or patterns for arithmetic processing depending on language modality. Next slide. We approached this question by using an EEG study using ERP to identify the components that are modulated by operation type and problem size in two groups, deaf early signers and English speakers. For deaf early signers, they were exposed to ASL lifelong, went to deaf school, and we presented both group subtraction and multiplication using a delayed verification design. They needed to respond if the answer shown was right or wrong. And the operations had different problem sizes, small, large, and extra large. Next slide. For both groups, we see similar effects for subtraction problem size on the modulation of the bilateral occipital ERP component. We didn't see a multiplication size effect. This modulation of the ERP component is focused on numerical quantity processing, processes that typically only occur in subtraction problem solving. Next slide. So the scientific and translational significance of the study. This is the first evidence of cognitive and attentional processing involvement for the operations, regardless of language modality used. Which is brain networks supporting arithmetic are not influenced by language modality. The math achievement gap that we see in the deaf population may be better explained by language deprivation, language delay, or social cultural factors in early home life. Maybe that is a better explanation than the language modality used. This finding is contributing to currently developing the first model for neural arithmetic processing in deaf signers. And next, we're going to look at deaf signers with language variation to see how this variability will affect arithmetic processing. Involved, for example, I got caught. Almost finished.
Sorry about that, Sarah. So close.
Yeah, I was pretty much done anyway.
Lovely presentation. You were almost over there, but you did get caught by the bison.
Mm-hmm.
Okay. Any questions for Sarah?
Thank you, everyone.
Thank you. Okay, for our next presenter, we have Lorna Quant. Are we ready, Lorna?
Are now? Okay, I'm ready. Hello, everyone. Today, I will be talking about a project that I've been working with recently about signing avatars and immersive learning. I'll be covering our recent progress and some of the challenges that we've had. This work is done with collaboration of two labs. My lab, the ABL lab or Action Brain Lab, working with ML2. Next slide. This project includes work in three areas, primarily embodied learning, secondly, virtual reality, using virtual reality goggles, and then signing avatars. So it's all three of these things that are creating and that we are using all three of these types of technologies and processes to support sign language avatars and immersive learning. I'm going to share some recent challenges that we have had with our work. In virtual reality, there are two types of signing and they look different. You can see from the photo here on the left, what you see in that image is that if someone is signing for themselves in first person, they would see their own hands, but there are some limitations in terms of being able to see one's own hands in the virtual experience, because there is a camera that films downward to some extent, but there's a limitation in the field. And so if one is signing in a certain area that the camera can catch, that's great. But if the signs are outside of the signing space of the camera, then there is currently a limitation with the technology we have to make sure that one's own signing is well represented in virtual reality. If you look at the image on the right, you can see how that affects what we see. The hand shapes are not clear. There's a lot of occlusion that happens. And we've identified a couple of issues. One of those issues is described more deeply in a paper that will actually be published this upcoming week. We also have been making some progress with our project as well. One big update that we have is our hardware update. We now have cameras that we can use in the VR experience that are able to track hand movement much more easily. We've been able to update the software as well, and we've seen tremendous improvements there. The second big update is that we have a new design for our teacher avatar. So the avatars that will be teaching ASL and VR look different than they did before. We've just completed that design, and you'll be able to see that as we move forward. Oh. Well, I guess you won't get to see what that looks like after all.
Yeah, it looks like the Bison caught you, Dr. Kwan.
Fair enough.
Well, maybe if folks have any questions about the design, we could...
Maybe we can click on the slide even if I don't say anything.
I think we'll give you a little bit of flexibility.
It's a good picture. All right, so just take a look. Thank you for asking. And that's it. Thank you. Thank you to the team as well.
Well, congratulations on this excellent project and the progress you've made. Very impressive. And it is quite quick, our time crunch here. Okay, any other questions before we move on? I think we are ready for our next presenter then. Okay, next will be Carly. Carly, are you ready?
I'm ready.
Okay.
Hello, everyone. I am Carly Leanna. I'm a PhD student in the Action and Brain Lab. Today, I will be talking about one study that ABL is currently running. We will be talking about how sign language experience, and especially the experience of being deaf, impacts biological motion perception. Research has shown thus far that native signers do have enhanced biological motion perception. And we want to understand where that's coming from and how that comes from the experience of being deaf versus knowing a sign language. Also, we wonder if that advantage that native signers have is only applied to a specific type of biological motion perception, or if that's true for all biological motion. Next slide, please. So this study is being conducted online, fully remote, with 300 participants as our goal. And it is still currently running. We have 3 different tasks. They go from a simpler task to a more complex task. In the first task, the question is for participants to answer using a keyboard and clicking one option or the other if the dots that they see are moving to the left or to the right for the most part. In the second task, They're asked to identify if the dots represent a person. And there are short clips of these videos that they'll see. In one image, it will clearly be able to be seen that it's a person. And in another, it may show that it's not a person. Participants have to make that determination. And in the third task, we ask if the action involves a ball. Again, a video clip will be shown where it looks like someone is swinging a golf club. And there has to be a determination if a ball is there. Likely there would be for swinging a golf club, but if there was the action of running, there would not be a ball. Next slide. Again, this study is ongoing, so we do not have the final results, but we do have preliminary results. And you can see from the images here, from the 163 participants we've had, if you look to the left, you can see the response time specifically of deaf people, and you can see their response time was the fastest. The lower the numbers are, the faster the response time, and we can see that difference. When you look at the graph on the right, you can see the response times for the action recognition tasks. And again, it shows that deaf people have the fastest response times in all tasks, from the simplest to the more complex tasks. We're very excited to see what our results will be moving forward, and that's it.
Wow, so close. The Bison did not catch you.
Yes. Big relief.
Well, congratulations, Carly.
Thank you.
Okay, do we have any questions for Carly?
Questions, anybody? All right.
Carly, who were your participants?
So I skipped that because I was rushing, but we need deaf, yes, good question. We need deaf, hard of hearing, and hearing participants, whether they know ASL or not. They can be anywhere from non-ASL users to fluent.
Excellent. So maybe in our audience, we have others who'd like to be participants, who know folks who they could send to your study.
Perfect. We already have enough non-signers, but at this point we are still looking for more signers. So yes, please click on the link that's now in the chat box.
I see it there. Okay, thank you very much, Lorna, for that information. Okay, any other questions? It looks like a very fun study.
Yeah, it is. It's watching videos, answering questions. It's pretty fun.
Okay, I think we are ready for our next presenter. Next up, we have Athena. If you wouldn't mind coming on the screen, please.
Hello.
Awesome. Okay, Athena, are you ready to get started?
I am. Hello, everyone. I'm Athena Willis, and I'm in my final year of the PhD in Educational Neuroscience program. This is my dissertation related to signing avatars, and I'm looking at do signers' perception of signing avatars change with different types of animation. This is an important question because, as you've seen previously, we've developed new teaching technology to teach new signers ASL. And we're looking at what the best application is to teach both deaf and hearing signers. Wondering how that fits with our findings in the lab related to variation in perception based on prior experience with sign language. We're wondering how that occurs in the brain, specifically looking at the sensory motor cortex and processing. We created 4 different stimuli that I'll show you on the next slide. As part of this study, We've seen that motion is an important variable in teaching sign language, and so we created 4 different stimuli that you can see what that looks like. The first is an ASL human, or a real human signer. Somebody could press play. She's signing salad. Next, we'll show you a clip of German Sign Language. This is a word that ASL signers don't know, but it's also showing natural human movement. If you could show the German Sign Language clip. So German Sign Language, with an ASL signer wouldn't be familiar with. And then the third is motion capture technology, biological motion that becomes 3D animation. So if you could show that clip. The avatar is signing Starbucks, which is more naturalistic motion. The third is computer synthesized. That avatar looks more awkward. The motion is not smooth. You can go ahead and see that. So you can see there's 4 different stimuli with the various range of familiarity with motion, as well as the words themselves. So now I'll show you what predictions we're making for this study. We gather behavioral plus EEG data. For behavioral data, we have 4 different variables: appearance, understandability of the signed word, natural movement, and the last thing that we're interested in is familiarity, and the amount of experience that a person has with that type of movement. You can see on the x-axis increasing familiarity. Oh, I got caught.
Sorry, Athena.
It's okay.
So close. Okay, are there any questions? Maybe about the last part of your slide of your presentation, perhaps? Okay. Looks
I
like
do
we have
see
a
one
question.
question. So why did we choose to use German Sign Language? That's a great question. So German Sign Language provided us with real human biological movement, but an unfamiliar sign language because they have a different grammar, phonological structure, and signed words that ASL users wouldn't be familiar with. And that provided us with a better control and understanding of how movements in Avatar change perception.
Okay, looks like we have one more question from Melissa.
So Melissa also asked, what did we learn from this study? So we learned if perception has to do with sign language. Also, if taking in mind embodied learning, embodied cognition, has to do with also the mirror mechanism. That way we can produce better educational technologies for signers.
Great. Okay. Thank you, Athena. All right. For our next presentation, we will have Melissa. Dr. Herzig, if you wouldn't mind, please coming up on the screen.
Hello, everyone. I am Dr. Melissa Herzig. I worked in the translational science lab for this study, I'm going to be talking to you about a collaboration we did with the Motion Light Lab, ML2. They developed the VL2 storybook apps. I work closely with them. I also work closely with Tom Allen and the EL2 lab before he retired. I collaborated with several other folks, including students as well. We specifically were looking at how the VL2 storybook apps support vocabulary development in children. And we wanted to understand what approaches would best support their learning. Next slide. We collected data from children ages 4 to 8. We have roughly 100 students, 100 participants. We do still have one more control group that we are working with now. All the students are deaf, and we looked at their signing levels and their vocabulary levels as we assess them. The students started with different levels of fluency. So we started with a pre-test and assessing their understanding of signs and fingerspelled words. They need to align signs and fingerspelled words with pictures or specific signs with other print words in English. If they saw the sign girl, for example, they'd have 4 images and they need to choose an image of the girl. All of these things all the stimuli came from the storybook, The Giant Turnip. There were 10 words in the pretest. We would have students watch the story, use the read app, and then use the mode where they were able to see the full story together, and then assess when we had all of this assessment done, then we were able to do specific instruction and then eventually assess with a post-test and to see if it made a difference, whether or not the teacher gave direct instruction or not, or if they just were indirectly exposed by seeing the vocabulary in the assessment. So in the vocabulary in the storybook app. So we assessed that pre and post to see what the differences were. And we also did post a week later to see what their retention was. We looked at how just seeing the storybook app and seeing these signed words in and of itself supported their language development. Wanted to have an understanding there. We also looked at whether or not a word was fingerspelled or signed, how well they did on the assessments themselves. If, for example, the word girl was fingerspelled versus if it was signed, how much of a difference it made in their assessment. We've been doing this study to understand the best way to help develop resources and continue to adapt to the needs of deaf and hard of hearing students and continue to do this type of work in the future. So that was the assessment we did, and that's it.
Well, congratulations, Dr. Hertzig. The Bison did not catch you.
Oh.
But I will tell you that the picture of the Bison is worth sharing.
Very cute.
Okay, so let's see if we have any questions for Melissa.
The question was eye tracking used? So it's something we could do. We have done that in previous studies. When Adam Stone was here, we did work with looking at Baobab specifically and seeing how readers would track information on the iPad if they were looking at a video being signed, English words, a combination of all. So we do have that data. We haven't processed it fully, and there's certainly more we could do to analyze that data and understand the eye tracking process. But that has been done with the previous study, but not in the current study that I was just describing. We're more looking at classroom use, teacher instruction. So eye tracking would be a little bit more complicated in the classroom. Though we did that with a previous app and another study. And if someone wants to use that data and run further analysis, we'd be happy to support that.
Well, quite an interesting study.
Yeah, I'm very curious to see the final results. Once we're done with working with the control group, we will be able to see that. We have already in our preliminary results seen improvement, especially with understanding of fingerspelled words, looking at the pre versus post and post assessments. For the students who already had some sign language vocabulary, we didn't see as much improvement, but we definitely saw an improvement in terms of fingerspelling reception, which we thought was an unexpected and very interesting result. So we're excited to see what more comes out of this.
Very interesting.
Thank you. Bye.
Okay, any other questions? All right. All right, I'm going to ask for the next group of presenters to join us. Great. So for this presentation, this will be a group presentation, and so you will have 6 minutes to present. So you'll be allowed a bit more time for your presentation.
Thank you.
Okay, ready to get started?
We are. Hello, everyone. I'm Dr. Bradley White, VL2 neuroimaging scientist. I'm not going to go into detail about the findings on this poster, but do check some of our earlier work we're presenting at CNS in San Francisco, California. This is supported by Gallaudet's research OSPRS Priority Research Grant. And we'll focus on the results and findings from 2 other projects. Ready? Next slide, please.
Hello, everyone. I am Chris Padilla, and I am the VL2 science manager here. So to talk to you about some of the studies we've done, there has been a belief for a long time that literacy required access to sound, but we know that deaf children do learn to read without that access to sound. We've been wanting to understand what has led to successful reading ability for those who speak and sign, and we wanted to understand the impact that this has had on their skill level. And so we've assessed this 3 different ways: through neuroimaging, through eye tracking, and looking at both orthographic and phonological tasks. We collected data from about 32 children, ages 5 to 7. We looked at those who were hearing non-signers and deaf children who both speak and were exposed to ASL at an early age. And let's show you our results.
Next slide. Thank you, Chris. Let's talk about what we found. Older hearing children were most correct for orthographic and phonological decisions, followed by older deaf and younger deaf, and finally, younger hearing performed least accurately for both types of decisions. Older deaf gazed at the correct word for most types of decisions, followed by older hearing. Younger deaf gazed at the correct word, and younger hearing at the incorrect word for orthographic decisions. And the opposite was true for phonological decisions. Accuracy and reaction time correlated with brain activation in the left inferior frontal cortex, or LIFC, brain activation in the LIFC, and posterior superior temporal cortex also correlated. These findings then suggest a cognitive advantage for sign-speech bilingualism and early reading. So keep an eye out for our posters of these findings that were accepted at IMBES in Montreal this July, and soon a paper. Next slide.
Exciting. So my name is Grady Gallagher. I'm a graduate research student here in VL2. So this is our second student in collaboration with a professor named Dr. Ben Bain, his gesture and literacy lab. We wanted to understand why some individuals understand gestures well, whereas others struggle and are resistant to understanding gestures. Ultimately, the goal of our study was to help support the success of students who are learning sign language and learning to understand gestures. So we used novel technology. We used a webcam that allowed for eye tracking. And also we coordinated that with behavioral and cognition experiments. So we wanted to monitor cognition, attention, and also participation in gesture. We had a 2x3 experimental design, which measured understanding and expressions of gesture skills for 3 different types of gestures, one being tangible gestures, the other being intangible gestures, and the third being neutral. So we began our pre-analysis. We had hearing participants entirely. We had a group of 5 monolingual participants and 10 bilingual participants, both ASL and English. And our findings were quite interesting. So Dr. White will be discussing our findings next.
Next slide, please. Thank you, Grady. A preliminary analysis found that ASL bilinguals used a wider visual attention area, or VAA, than English monolinguals overall. And we also observed this pattern throughout the data. And the larger VAAs appeared related to higher accuracy and smaller VAAs to lower accuracy. Again, this is for gesture. And bilinguals were more accurate when perceiving gestures, whereas more monolinguals were more accurate but slower when producing gestures. Bilinguals were more accurate when perceiving and producing neutral gestures, so no semantic context. For example, the shape of a triangle. Monolinguals were more accurate when producing intangible gestures with low semantic context, like surprised. And we hypothesize that these fascinating differences may be due to ASL semantic interference in bilinguals. So both groups were most accurate when perceiving and producing tangible gestures with high semantic contexts, for example, drinking. And these findings help us to understand some of the complex factors involved in gestural use, language experience, attention, also working memory. So keep an eye out for these poster findings at IMBS this July. Thank you, everyone. We wish that Dr. Petito could be with us today, but unfortunately she was not able to make it. And you'll see all of our research partners listed at the bottom of this slide. Thank you again, everyone.
Thank you.
Thank you. Thank you to the entire VL2 team. The Bison did not catch you today.
It was close.
Well, thank you. That information was just incredible. What wonderful research.
Thank you.
So does anybody have any questions for the group?
I did see one in the chat. Shahir asked us about what algorithm we use for eye tracking. Now it depends on which study you're asking about. For the first study, we used Tobii eye tracking, and we used their proprietary algorithm for processing the data. For the other study, we used LambVed, the online webcam eye tracking, and we used their proprietary algorithm for eye tracking. And then we took the raw data and processed data, and then we processed that ourselves in MATLAB and PenLab. And what you see in the results for children, we're looking at a ratio of gaze at the right word compared to gaze at the wrong word. For the adults, we're looking at actual density plot for each pixel.
And I see a question from Glenn as well. What is the potential application for, I'm not sure which study you're referring to, Glenn. Do you mean the adult study we were talking about recently?
So one of the motivations for our gestural study was, if you watched our talk from last April, the motivation is working with Ben Bain and his gestural literacy lab. And their goal is to develop an actual assessment that can be used to test people's gestural competence. We also suspect that could be used to test someone's willingness or resistance or their potential struggle with utilizing gesture.
Well, I have a question. This is Rachel.
Sure.
So if we're thinking about training programs out there and maybe how that could maybe enhance use of gesture, what do you think would help to train individuals on understanding and using gestures?
That's an interesting question. Our original hypothesis is that maybe sign language would help. So if a person has an experience with the visual language, maybe sign language would help a person with gesture. But our results show that it's actually much more complicated than that. People who don't know sign language tend to struggle with specific areas of gesture, but the opposite is true for signers. They also struggle, but just in a different area. So I'm not sure that we really have the answer yet.
Hopefully we will soon.
Yeah, but we're getting close.
Certainly. Okay, any other questions about our recent presentation?
And feel free to email us if you have other questions that come up later.
Absolutely. Okay, well, very exciting work.
Yes, thank you.
Oh, I may see one more question in the chat from Melissa.
Mm-hmm.
Yes, gesture is a very broad definition. In our literature review, there's also a lot of there's not a lot of research done on gesture. So it was difficult to categorize and think about where to start. So we tried to think about what makes people either unable to or resistant to use gesture. And we have some guidance of what we chose, why we chose it, and what we were looking at. We thought maybe some gestures might be harder than others. So we had intangible, tangible, and neutral. And we did see some performance differences across categories. And then we thought maybe it's motion related, or maybe it's expressive versus receptive. So we did that with the 2x3 design, looking at receptive questions and expressive questions. And we did find differences between groups there as well.
And then one thing that comes to mind in terms of an application for this study is that finding that certain types of gestures may be easier for people to pick up on. So that would inform us in terms of teaching. So if somebody is teaching ASL or teaching gestures, or maybe just using gestures in general, then maybe someone would feel more comfortable using certain types of gestures. So we can use this research to justify why we're actually using certain approaches in our teaching to support learning.
Related to that, we did find that both perform similarly very well for tangible gestures. Those gestures have high semantic context, for example, drinking or money, eating. What's another example? Things that are physical, tangible, that you can touch and hold, things that are more concrete objects. People typically have more accuracy in those gestures compared to more abstract or less semantically tied gestures.
Okay, well, thank you.
Thank you.
Yeah, sure, Melissa.
Okay, I see that Melissa let's comment from Melissa in the chat.
Yes, happy to. Let's get together.
Yeah, always nice to see some connections happening. Okay, so this will be our last presentation for today. All right, thank you. All right, are we ready to get started?
Yes, ready. Right, hello everybody. I am Melissa Mouse-Kuhn, and I am the director of the Motion Light Lab. You can see there my team. Everything we do is done with the support of the team. The Motion Light Lab is a little bit different in that we are not as research focused, that we do partner with the other research labs that are part of VL2, but we are doing some other exciting work supporting the work of the other labs, and we're focusing more on development. I'd like to talk about a few highlights from ML2. We have worked with a focus on social change, and we are in a 15-month program with Ashoka and IKEA. We also worked with the Harvard Advanced Leadership and the Institute on Social Impact Hackathon, which was a great opportunity for networking and shifting narratives. Our biggest goal is to make sure that deaf children have access to sign languages and to have the resources that we've created shared through our networks to make a greater impact. We've just completed 2 years worth of Storybook app trainings. Over 150 people have now been trained on how to create these Storybook apps. Next slide. Next slide. There are 2 teams at deaf schools that were actually able to create and are now distributing their own apps that they created through the Storybook programs. They are available in the App Store, and I highly recommend you download these apps. Next slide. Our 3D animation work continues to advance and grow. Our goal has been to create fluid signing 3D characters. This is important for application in gaming, VR, AR, the metaverse, and beyond that. The future is a digital experience. When we think about immersive learning, we have to have fluent signing avatars in these virtual spaces. We got funding from Sorensen Communications, which allowed us to develop and create a short film. You can see it here. It's called Dimensions. It has been accepted to several film festivals globally, and we are now showing our film there. Next slide. Another very exciting change for us is that we have been able to expand the size of our motion capture lab. We were in a very small space and allowed only for one person to sign at a time. Now we've moved to a much larger motion capture space. It's a 20 by 20 space, and that we have a second faceware system as well, so that we can now start testing signing dialogues that can happen between 2 people in motion capture. So this is incredible technology. You can see a photo of that shift that's happened. Next slide. And the big announcement I'd like to end on is that we have now this incredible opportunity working with Pigmental Studios and they are an animation company, and we are developing a television show. It will be coming out in the next couple of years. Plan for distribution is 2024, and it's a children's TV show called The Bison. Luckily, I was on the last slide. The last slide. I'm relieved I made it that far. That's still good. Yes, I'll take it.
Melissa, you can continue.
Are you sure? I can finish my comments there.
Please.
Okay, so we are working on a television show with deaf and signing characters. And this is a show called Here Comes Mavo. The character Mavo comes from the first VL2 storybook app, the Baobab. Mavo is the character from that story, and it's very exciting to be able to see that. We're looking forward to that. If you have any more questions, feel free to ask. Also follow us on social media, Instagram, Twitter. We are often posting information and updates. We're happy to keep you abreast of what's happening. Thank you, everybody.
Excellent. Wow.
I can finally breathe now.
Take a big breath.
I don't think I took a breath that whole time.
Okay, do we have any questions?
Yeah, feel free to ask any questions if you have them. It looks like most people are just very excited about the TV show that's coming.
Yeah.
Taking a look here. Great.
So ML2, what's the 5-year plan?
What is the 5-year plan? Conrad, good question. What is our 5-year plan? Well, the television show being distributed, that is now in the works. Our 3D studio must continue to grow. There's a lot of new technology out there and constantly more that becomes available. Our lab is the perfect place for us to see how we can use the technologies that exist from a deaf lens and a deaf perspective. And we look forward to continuing to do more work like that. We will certainly be collaborating with other researchers and other labs. In our collaborations, we've mostly worked with ABL and TL2, and we will be working with Rachel's lab, looking at math anxiety and creating some storybook apps there. So we enjoy the collaborations we have with other labs in VL2. It's been a wonderful experience. And we also look forward to more social impact, continued impact, especially with hearing parents who really want to learn how to sign. We want to have a plethora of resources for them ready to go as soon as they're open to it. And we hope to continue sharing more of that over the next 5 years.
Wow. Well, that is so exciting.
It is. Thank you. Oh, I do see there's another question there. I see that now. Yeah, I can sign the question that's here. So the question is, what's the process of getting the show out as a television program? That is a great question. So there is a fairly extensive process. We are now and have been in the development stage, coming up with our vision, our content, specific stories, characters, developing the world, developing the scripts. We create what's called a Bible for the television show and a curriculum as well to make sure that the show has educational components and values that allow children's learning to be supported. And so we have those things pretty much set. From there, we move to production. Production is also quite expensive. So we are looking for a distributor. And once we contract with a specific distributor, and we are going big, we're not looking for a small company with limited distribution. We are going big. So we are looking for the budget that comes from the distributor in order for us to complete production. We have not signed with a specific distributor, but there are a number of meetings coming up and you can watch for more updates on that soon. One other thing I will mention as well, the more that we develop, the more we'll be able to have control on our framing and content when we develop these things before working with a distributor, talking about centering sign language and deaf people. And if we only have a basic idea, that means that the distributor then gets more of an impact on the creative content. So it's been great to be doing this process so far, and we look forward to what's to come. Hope that answers your question.
Okay, any other questions?
I don't see any other questions.
Well, that's a great description.
And if not, then I will turn the show back over to you, Rachel.
Okay, well, thank you, Melissa. All right. So now we will open the floor for any general questions about any of the presentations that you've seen today. If you have any specific questions for any of our presenters that you weren't able to ask earlier in the program, now is the time. Any questions, comments? Okay, looks like Ilaria would like to make an announcement.
Okay. If there's no question, I just wanted to share an announcement while everyone's here about our new summer school next year. We will have our first VL2 Penn summer school in cognitive and educational neuroscience. And we'll be inviting undergraduate students to come for 6 weeks.
Very exciting.
And learn different neuroimaging techniques. All undergraduates will be able to experience working in different labs with different neuroimaging techniques and learn, basic important context and content to get ready to transfer to the whatever university they're going to and put that on their CV so that they can become our future researchers.
Amazing. Well, congratulations, Ilaria.
Yes, we're collaborating with all of the Penn labs.
How exciting. I'm really excited to hear about that.
Next year.
So I can share that way back when we had, when I was an undergrad, I was a part of that experience. So I was a student in REU, and I had a summer experience. And that was such an important part for me. because it allowed me to continue to do research.
Right, and that's the goal, really, of this summer school, is to provide that initial knowledge and initial interest, that hook, if you will, to the next group of students, so that they can stay, and maybe also decide what classes they want to take for the next year and modify their educational path.
So great. Wow. Well, congratulations. Okay, any other questions, comments? Okay. So first, I would like to thank all of our presenters today. And I know that these presentations represent a lot of hard work. And they represent work from professors, from students, research assistants, work from the entire team. And I think that our understanding of science is happening as a team, and certainly requires collaboration. So thank you, Melissa. So I thought that this experience, seeing all these presentations, the sharing of ideas and research findings, is so exciting. And I think it's a wonderful way to end the semester and to celebrate all of the work that we've been doing together. So thank you to our entire team. I'm so appreciative. Thank you to our audience today. Thank you for sharing and working with us in sharing our science and our findings. It has been so exciting. Okay, so I think that is about it. Thank you once again. Bye-bye, everyone. Thank you, and see you soon. Oh, and thank you, of course, to our interpreters as well. We worked with a fantastic team of interpreters, and we're really so appreciative of your work. Thanks, everyone. Bye-bye.